So quickly reiterating what we've talked about, you've got a function, fx, which if we derive, you'll get another function, which is related to the function, and we call this function the first derivative. By definition, is the rate of change of the function. So graphically, this would represent the gradient of the tangent to fx. There are special terms that we need to be aware of. Those are increasing, decreasing, and stationary. Increasing simply just means the first derivative is strictly positive, not equal to 0. Decreasing just means the first derivative is strictly negative, not equal to 0. And stationary just simply refers to first derivative equal to 0. And your stationary points refer to that. Now we also have second derivatives that we'll need to talk about. So if we take your first derivative, which is a function, and derive it again, you will get another function called the second derivative. Represented by f double dash x. For reasons we have outlined, this simply represents the concavity of the function fx. And so that's a very important point to remember. First derivative is the gradient of the function fx. Second derivative is the concavity of the function fx. And likewise, it also has specific cases when it's concave up, concave, referring to concavity. So you think of the second derivative being positive, concave down, and you think of second derivative being negative. And those are specific cases. Do you notice anything that we're missing? We've talked about concave up, second derivative being strictly positive, concave down, being second derivative strictly negative. Are we missing anything?
Can it be equal to 0?
Right, there's got to be a case of when it equals 0. All right, there's got to be that case that we haven't talked about yet. So I will briefly mention it right now, but we probably will not focus on that right this moment. Hopefully we will later today. But when the second derivative equal to 0, this is when you might tie in with inflection points. But there is a question mark there, all right? But this is what we've covered thus far. Now we will apply it to our stationary points that we talked about before. So just to demonstrate the point in a relatively quick manner, let's look at something easy. So consider y equals x squared, all right? Now we all know what the graph looks like. I'm just going to draw it out very quickly. It looks something like this. Is there a stationary point here?
Zero.
And the answer is yes, at x equals 0, which means y equals 0, so it's at 0, 0. Now, what type of stationary point is it?
Minimum.
Right. Now, we all know the answer. We all know that's what it looks like. We all know that's what, the answer is. But let us now do it again, but using the calculus. So by definition, the stationary point is where y dash equals 0. So we obviously solve for y dash being 2x. We let that equal to 0, which gives us x equals 0. Simple enough. Your next step is to sub x equals 0 into y equals x squared to give us 0 squared, which is 0. Therefore, now, my question now is, what type of stationary point is it? Now, we know the answer. We know the answer is a minimum. And we also know that we could do it the way we said before, which is work out the gradient to the left, the gradient at the point, and the gradient there, and get a changes in this way and get you a minimum. And we could do that. You guys there?
Yes.
Yeah. Right? It's a stationary point, and we know the answer is a minimum, but think about the concavity. What is the concavity? Slides which are now lost, but just think about your sort of stationary points. You know, you've got different types. You've got your minimum, your maximum, and your horizontal point of inflection. Now, we're just ignoring these for the moment. Just ignore these. Just keep with the turning points for the moment. So your minimums roughly all look like this, right? And your maximums all look like this, right? So for a minimum, what's its concavity?
Up.
Right. And for a maximum, what's its concavity?
Down.
Now, is it possible to have a minimum with being concave down?
No.
No, right? Because, you know, if it's concave down, well, it's not the minimum. It's not the maximum. There's just more to go if it's concave down. It doesn't matter if it's concave down like this, in which case it's a maximum for sure somewhere, or if it's concave down like this, as we talked about, or like this. The point is, I mean, it's simply not going to be the minimum, right? I mean, if it's concave down, there's just not the minimum. So for a minimum, it's got to be concave up. And for a maximum, it's got to be concave down. And what does concave up mean mathematically?
The second derivative is positive.
And concave down? Yeah, concave down means?
Negative.
In other words, we have now identified a second way to work out your type of stationary point, ignoring horizontal point of inflection, which is a little bit ambiguous. You can probably tell that what you would need is the second derivative equals 0, but we will talk about the fine details of that in a moment. There's a bit of a warning sign I need to put up about that. But, and those warning signs normally don't get triggered in SL, so you probably don't need to worry too much about it, but I do have to tell you about it when we do it. So what type of stationary point? Well, we could either do method 1, which is use table of values, and you guys have practiced already, but method 2 is simply use the second derivative. So employing that method here, I'm going to work out the second derivative, which will simply be 2. And is 2 positive or negative?
Positive.
2 is a positive number. So given that, I now have this scenario. I have already worked out that at point 0, 0, I have a stationary point. I've also worked out at this point, it's, you know, at x equals 0, or any x for that matter, the second derivative is positive, which means it's concave up. So it's a stationary point, but because the second derivative is greater than 0 and it's concave up, that allows me to then deduce, without knowing what it looks like, that 0, 0 is a minimum. Does that make sense?
Yes.
Good. So let's now just quickly draw up a nicer, neater version of this. So a minimum and a maximum and a horizontal point of inflection. Minimum looks kind of like this. Maximum looks kind of like this. Horizontal point of inflection looks, well, kind of like that. All of them are stationary points. And all of them will therefore have a first derivative equal to 0. If we want to tell what type of stationary point I have, then one way to do it is to use the second derivative, which represents concavity, which would mean this is positive, this will be negative, and this will equal 0.